I welcome you all in this new video series, and this is the first part, and this is actually a fresh start of organic chemistry. So I will start from the very beginning, and in this lecture, I will discuss about the basics of organic chemistry. So before starting our today's topic, I want to make sure that you know about these topics. So whatever written in the screen, the structure and bonding, the delocalization and conjugation, and acid base. You should have at least the basic idea about these topics. Otherwise, you cannot understand our today's lecture. So, if you don't have proper knowledge about these topics, I will advise you to go through these topics from anywhere and then come back to the lecture. So, having said that, let's start our today's topic. So these are the things which you are going to learn in this lecture. The electronic effects, which include resonance, inductive effect, and hyperconjugation. Then we will talk about steric effects and its application. Basically, I will talk about the application of steric effects uh, with regards to the in regards to the acid base property. There are many other application of steric effect, but I will not discuss that here. We will discuss that later. In this case, we will discuss about the effect on acid base property, and then we will go to the stereochemistry part. First, we are going to talk about electronic effects. What is electronic effect? Now, this is a very important topic in organic chemistry, the electronic effect, because in organic chemistry, basically uh, we study the reaction of different compounds, product formation and reaction, right? So, whether a reaction will happen or not, and if the reaction occurs, how fast it will how fast it will happen, or what will be the mechanism of the reaction, what will be the reactivity of certain compound, that is highly dependent on the electronic distribution and the electronic effect in the starting material, and more precisely the electronic distribution in the bonds which are included in the reaction. And we are talking about sigma and pi bonds. So uh, that are the main things about electronic effects. Now, there are three kind of effects: resonance, inductive, and hyperconjugation. First, we will start from inductive effect. What is mean by that? As the name suggests, inductive effect means uh, induction of something, right? So, this is one example given here. See, this is one example, HCl molecule. So, in HCl molecule, if you see, because hydrogen and chlorine, they are not the same atom, they differ in electronegativity. So there is a redistribution of electron cloud in the HCl bond. Chlorine, being more electronegative, acquires higher negative charge, whereas hydrogen, being less electronegative, it acquires partial positive charge on it. And this is the main concept behind inductive effect. Now imagine when the same chlorine will be attached to carbon atom, what will happen? So see here, the same chlorine is attached to carbon atom, and chlorine is also more electronegative than carbon, so it will pull electron from the carbon, and that will induce positive charge on that carbon atom. So uh, when we study inductive effect, our reference is the carbon atom, and if a more electronegative atom is attached to carbon, it may be chlorine or any other halogen. So you have halogen, it may be oxygen based group and nitrogen based group, then they will pull electron from the carbon, the reference carbon, and induce positive charge on that carbon atom. So this thing we call minus I effect or minus inductive effect. Whereas if you have a silicon group which is electropositive or less electronegative than carbon, then it will push electron towards that carbon. Or it may be some other alkyl group, they can also push electron towards carbon. So this is called positive I effect or positive inductive effect. So together it is called inductive effect, and when something push electron towards carbon, we call it plus I effect. When something drag or pull electron from the carbon, we call it minus I effect. So this is all about inductive effect. Now there are some important points which we should remember about inductive effect, and that is inductive effect operates through sigma bond. It is operating through sigma bond. So distance is an important factor here. As we go away from the carbon to which the group is attached, then the intensity of the inductive effect will decrease. So you can see in the first carbon atom, it has the highest amount of positive charge, delta plus. As we go to the second carbon atom, it is delta plus. That means the intensity of the charge is lower. In the third carbon atom, it is even lower, and in the fourth carbon atom, there is practically no inductive effect. So up to third carbon atom there is inductive effect. Beyond four carbon atom there is practically no inductive effect. So this is the limitation of inductive effect. And also inductive effect is not very much powerful. Okay, we will see that resonance is much more powerful. And the last two things which we have to remember is, because plus I effect means it is pushing electrons. So whenever you have a group with plus I effect, they will stabilize electron deficient center like carbocation or carbene, like that. Or whenever you have minus I effect like chlorine or other halogen, it will stabilize um, carb anion or other electron rich species. So these are the points you should remember from the inductive effect. Now let us move to our next effect, that is resonance or mesomeric effect. So resonance effect, it is also one kind of electronic effect, but in this case this operates through the pi bond and not through the sigma bond. So presence of pi bond is crucial for the resonance. Now we can understand the resonance effect by looking into this compound. So we have a pi network here. Now this pi network can be larger, or it may be like this. So it may be, so the pi network can consist only one pi bond, or it may consist more than one pi bond. That does not matter, but presence of pi bond is very important. Okay, so whenever a pi bond is directly attached to a group like OH or NH2 which is having lone pair, what will happen? It will push its lone pair into the pi system, and that will induce negative charge at the terminal, right? So it is pushing electron, and that's why it is called plus R effect or plus resonance effect, right? But whenever a group which is not having electron pair but having low energy orbital or vacant orbital, they will actually pull electron from the pi system, like this carbonyl group over here, or you may have NO2 group. These groups will pull electron from the pi system, and this we call minus R effect. So these are the groups having lone pair, they will show plus R effect, and these are the group having vacant orbital or low lying vacant orbital, they will show minus R effect, right? What are the, so when we talk about resonance or mesomeric effect, aromatic rings, they plays very important role. These aromatic rings, you can see, they can show both plus R and minus R effect, because uh, they will change their behavior depending on to which group they are attached. For example, in the first case, this benzene ring is attached to some electron rich center, so it is uh, pulling electron from that center. So in this case it is showing minus R effect, whereas in the next case you can see it is attached to some positively charged center, and in this case it is pushing electron towards that center, so now it is showing plus R effect. So this is very important. And same is the case with allyl groups, they do the same like the aromatic rings. So this has some consequences. What is the consequence? So by using this thing, we can tune the reactivity of these aromatic groups or these allyl groups. How? So let's say we introduce some OR group or O minus group in the aromatic ring. So then what will happen? Because of the lone pair of this oxygen, it becomes a better plus R group. Similarly, if we introduce nitro group in the aromatic ring, what will happen? See, if we introduce nitro group, then you will see that it becomes a better minus R group, because now it will drag electron into the nitro group. So this becomes a better minus R group. So we can tune the plus R or minus R capacity of the aromatic ring. This is very important. Now these are the important points about resonance. So first of all, resonance is operating through pi bond and not through sigma bonds, and that's why it does not depend on the distance. So let's say you have a big pi system like this, and at the terminal you have this, let's say, nitro group. Okay, so now when this nitro group will pull electron, it will pull same amount of electron from all the centers. So it will induce same positive charge over here, same over here, same over here, same over here. It is not like um, at the third carbon atom it will be less, and beyond 4 it is 0. It is not like that. All the carbon atom, as long as they are conjugated, it will face same electron pull or same electron push. So this is very important. Resonance effect is independent of distance. Okay, and the next point is resonance is much stronger than inductive effect. And plus R effect, because it is pushing effect, it will stabilize carbocation and other electron deficient species, whereas minus R effect, because it is pulling effect, it will stabilize carbanion and other electron rich species. Now the next thing is captivative effect or push pull effect. So when you have a minus R group and a plus R group, they are attached in the same pi conjugated system and they are conjugated, then there is an extended resonance. You can see from here to here there is an extended resonance. You can see there is an extended resonance, and this phenomenon is called captivative effect. Similar captivative effect can be observed here. So from this nitrogen lone pair to this, there is an extended resonance. Similarly, from this sulfur lone pair into this cyanide group, there is an extended resonance. So this is called captivative effect, and this is a very strong effect. Now the third electronic effect is hyperconjugation, and it is sometimes also called no bond resonance or sigma donation. And in this case, what happens when you have a carbocation and you have some alpha CH3 or other alkyl groups, then this CH3, this CH bond, it can donate its sigma electron into the unfilled p orbital or the carbocationic center. So this is how the resonance will go. So there are 9 conjugable hydrogen atoms over here. Okay, and not only with the carbocation, the hyperconjugation can also occur with the adjacent pi system, right? So and adjacent aryl system. This is how hyperconjugation can also occur. So hyperconjugation, although it is not a very strong effect, but in some cases it becomes the deciding factor, and we will see that later. The next point is field effect, which is also some sort of electronic effect, but this effect does not operate through any kind of bond. It operates through space. It operates through space. It does not need a bond, and that's why it is called field effect. So you can see there is no direct communication between this chlorine and this carboxylic acid group, or this chlorine and this carboxylic acid group. There is no direct bond, but the difference between this compound 1 and compound 2 is, in compound 1 this chlorine and this carboxylic acid group, they are in the same side, whereas in compound 2 they are in the opposite side. So that has consequences on their acid strength. So when these two compounds shows their acidity, so it will lose its proton and it will become carboxylate. This will also become carboxylate. Now in the first carboxylate, because the chlorine and this carboxylate anion, they are in the same side. Now the chlorine will acquire partial negative charge because of inductive effect, so there will be coulombic repulsion between these two because they are in the same side. But in case of compound 2, they are in the opposite side, and that's why there is no such repulsion, which will result in higher acidity for compound 2 compared to compound 1, which is manifested in their pK values. So this is a very important example of field effect. The next topic which we are going to discuss is the steric effect and its application. So we will talk about only the steric effect on acidity and basicity. Now here we are having two compounds, basically one amine NR3, which is forming adduct with some BR3, boronic Lewis acid. So now this amine is Lewis base, and sorry, this amine is actually our Lewis base, and this sorry, this Br3 is our Lewis acid because it is having vacant orbital. Now they will form adduct. In both cases they are forming adduct, so they are forming some adduct like this Br3 NR3. Now in the first case the R3, for nitrogen the R group is actually the ethyl group. These are ethyl groups, and for boronic compound it is BME3. In both cases it is BME3, but in first case the amine is triethylamine, but in the second case it is cyclic amine, which is similar like triethylamine, but you can think it as if the triethylamine is tied in the back, so it cannot move freely. Now what will be the consequence? The consequence is, because it cannot move freely, the hydrogen atoms on the cyclic side, it is apart from the hydrogen atom of the methyl group of the boron. Whereas because in the first compound the triethylamine, that ethyl groups can move freely, they will encounter with the hydrogen atom on the methyl group of the boronic compound, and this will create steric hindrance, and that means this adduct 1 is less stable and adduct 2 is more stable. So that makes this triethylamine less basic and this cyclic amine more basic. So this is effect of steric effect on the acidity and basicity. So this is in this case it is on the basicity, of course. Now the next thing, so here we are talking about the effect of steric hindrance on acidity. So in these compounds, all these compounds, they are called proton sponge. They are very interesting compound. They have many applications. So what is the specialty of these compounds are the nitrogen lone pair is there, which will take the proton, as in the case of this compound you can see, but their surrounding, you can see their surrounding atmosphere is very bulky. Two ethyl groups, then this OMe group, in this case two methyl groups, here this large aromatic rings, here this large tertiary butyl group. So in all cases the nitrogen center, which is actually the basic center, is surrounded by large groups, and that makes this compound special. They can only take up proton, so they take proton like a sponge. If you introduce water to a sponge, it will soak water. Similarly this compound will soak only proton, it will take only proton. That's why they are called proton sponge. For example, this compound, we can see there are four nitrogen center and proton can be inside them, okay, like this, but no other thing can enter inside this, or no other thing can interact with this nitrogen. So they are specially designed for the proton, and that's why they are called proton sponge. These are some more examples of proton sponge. So what is the specialty about proton sponge? So let's say we want a reaction where we want a base which will only take proton and nothing else, then we can use this proton sponge. They are very effective. Now another most important or interesting thing is the steric inhibition of resonance. So we have aniline, in this case substituted aniline. So this is normal aniline, Let me draw it again. So I am using this pencil mm, for the first time, that's why it is creating some problem. This is the aniline, and this aniline, aniline is basic, but it is slightly basic. It is not as much basic as its counterpart, like aliphatic compound. Let's say you have this aliphatic compound, amine. It is much more basic, but this aniline is much less basic. Why? Because the nitrogen lone pair is delocalized into the aromatic ring, and that's why its basicity is lower. The lone pair is not available for the proton. And what happens when you introduce a nitro group in the ring? So the basicity will even decrease because of the minus R effect of that nitro group, because nitro group is present. So even more delocalization of this lone pair will take place into the ring. So it will be very less basic. But what about the basicity of this compound? We have three nitro groups. So whatever we know till now, we will say that this compound will be very less basic, because all these three nitro groups will drag electron from this amine or from the nitrogen lone pair. But in reality, this compound B is much more basic. Now, what is the reason? The reason is clear when you look at their structure. So in compound A, as expected, the delocalization will take place. But in compound B, you can see in compound B, the delocalization cannot take place. Why? Why the delocalization cannot take place? Because of the presence of these large methyl groups on the nitrogen, and the adjacent large nitro groups, they will sterically interact with each other, and it will rotate the plane of this NME2 group. So now the nitrogen, the p orbital, the field p orbital on the nitrogen atom of the NME2 group is no longer parallel with the p orbitals of the ring, the aromatic ring, or with the other nitro group's p orbital. So it is no longer parallel. In fact, it is perpendicular, and that's why delocalization cannot take place, because being parallel is the most important condition for delocalization. So no delocalization means the lone pair is readily available, and that's why it is much more basic than we expect. But what about this compound? In this compound also the similar situation, and this compound is very less basic. Why? Because in this case you don't have large Me2 groups, rather you have only NH2 group, which is very small. And in fact, in this case, because of this hydrogen bonding here, you can see this hydrogen bonding with the hydrogen on this NH2 group and the nitro group. This hydrogen bonding will make sure that the nitrogen is in the same plane with the aromatic ring, and there is a very nice delocalization. You can see there is a very nice delocalization. All the orbitals are in the parallel position, and this delocalization means the nitrogen lone pair is no longer available to show its basicity, and that's why this compound is very less basic. So this is very important. Now we come to the end of our today's lecture, and if we summarize our what we have learned today is, electronic effect is very important in deciding whether a particular compound will react or not, or if it react, how fast it will react. And also steric effect plays important role in determining the basicity and acidity of a molecule. So that's all for today. Thank you for watching, and stay tuned for the next lecture. A best of luck for you.